In this lecture, we introduce the bisection method for estimating what we assume to be the unique solution x equals r of the equation f of x equals 0. Let the root r be on the interval from a sub 1 to b sub 1, where f is continuous and that either f of a sub 1 is less than 0, while f of b sub 1 is greater than 0, as is the case for the graph to the left, or that f of a sub 1 is greater than 0, while f of b sub 1 is less than 0, such as on the graph to the right. These two inequalities combined is equivalent to the condition that the product of f of a sub 1 and f of b sub 1 is less than 0, since f of a sub 1 and f of b sub 1 have opposite signs. We will have to modify this key inequality later in the lecture when we make the generalization for the interval from x equals a sub n to x equals b sub n at the nth iteration. We will provide a justification for the need to modify this inequality. With f being continuous on the interval from a sub 1 to b sub 1 and f of a sub 1 and f of b sub 1 having opposite signs, we can apply what is called the intermediate value theorem. The intermediate value theorem states that if f is a continuous function on the interval from a sub 1 to b sub 1, and k is any real number with either f of a sub 1 is less than k is less than f of b sub 1, or that f of a sub 1 is greater than k is greater than f of b sub 1, then there is a value r on the interval from a sub 1 to b sub 1 such that f of r equals k. For this lecture, the value of k is 0. We now write down the steps for the bisection method. The first step is to find the midpoint, which we call c sub 1 of the interval a sub 1 b sub 1, hence the name the bisection method. C sub 1 is equal to half of the sum of a sub 1 and b sub 1. C sub 1 is also the first estimate for the root r. There are now two half intervals to consider, one on either side of c sub 1. In step 2, we determine on which of the two intervals we continue to find the next midpoint estimate for x equals r. To determine which half interval it is going to be, we check the sign of f of c sub 1. More precisely, if the product of f of a sub 1 and f of c sub 1 is less than 0, so that 0 is between f of a sub 1 and f of c sub 1, then the solution x equals r is on the interval from a sub 1 to c sub 1. This is certainly true for the left graph. If the inequality is true, then we keep the closed half interval a sub 1 c sub 1 and throw out the other half interval. And so a sub 1 becomes the new left endpoint a sub 2, while c sub 1 becomes the new right endpoint b sub 2. On the right graph, the product of f of a sub 1 and f of c sub 1 is greater than 0. In such a case, c sub 1 becomes the new left endpoint a sub 2, while b sub 1 becomes the new right endpoint b sub 2. We had mentioned that we must modify the key inequality that the product of f of a sub 1 and f of c sub 1 is less than 0. This is if we are to generalize these two steps for all the iterations of the bisection method. The reason for the change is that it is certainly possible that at the nth iteration, a sub n turns out to be equal to the exact solution x equals r. If so, f of a sub n would be equal to 0, and the product of f of a sub n and f of c sub n would also be equal to 0, so that the inequality would be false. And this would mean choosing the half interval from c sub n to b sub n, and throwing out the other half interval including its left endpoint a sub n, which we are supposing is equal to the solution x equals r. Of course, we want to keep x equals r. And so to avoid throwing out the solution, we change the inequality from a strictly less than inequality to a less than or equal to inequality. Then we repeat these two steps, etc., 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 and obtain the sequence of midpoint estimates whose limit is the solution x equals r.